Hello, it's Dumplet here. Here's an item on number theory. X is a real number such that the floor of x over 100 times the floor of x over 100, that's going to be equal to 5. So this expression with a nested floor function, pretty interesting. Anyway, so try to get all the values of x. Credits to the Art of Problem Solving community for this item. As usual, pause this video if you'd like to give this item a try. But if you're done, let us dive into the solution. Alright, so whenever we have an item that deals with the floor function, technically we want to incorporate maybe writing in terms of some things. So for example, we might want to consider the integer part because we have a lot of floor functions, and maybe consider like the range of values. So those are the typical techniques that we're going to apply here, and particularly what we're going to do first is to set a value for the floor of x over 100. So what we're going to do here is the following. So let's just say the floor of x over 100, that's going to be equal to a. And let us try to consider like the range of values. So if the floor of x over 100, let's just say it's a, the only thing we know about a is that it's an integer. So we can get a range of values for x over 100. By definition, I guess this should be this should be greater than or equal to a and less than a plus 1, because the floor of x over 100, that's just going to be a. And what we're going to do here is the following. Now, we have this equation, and we are going to manipulate this equation to look something like this. Because we have the nice floor of x over 100 equal to a, apparently if I multiply the x over 100 by the floor of it, it's going to look something like the inside of this the inside of this outermost floor function. So I'm going to multiply both sides by floor x over 100. So obviously the inside just becomes x over 100 times the floor of x over 100. And well, the floor of x over 100, we set it to be a. That's why a here becomes a squared. And then a plus 1 here from a plus 1 times a, that becomes a squared plus a. And here, because we know that the floor of this value, it's going to be 5, we can kind of get a range of values for this value in the middle. We know it's going to be greater than or equal to 5 and less than 6. So at least we would get a nice range of possible values, even in the extreme case for a. So in the extreme case, a squared can go almost 6, and in the extreme case, a squared plus a can go as low as 5. And we are going to take, we're going to solve for a, and hopefully the intersection of the two, which is what we want, will kind of allow us to get what the value of a is. Because we know a is an integer, so at least in the range of values, we're going to pick some values of a, and we can work from there. Alright, so we have the two, a squared less than 6 and a squared plus a greater than or equal to 5. And so the first one and the second one, they're both just quadratic inequalities. So the first one that's going to give us a must be strictly between negative square root of 6 and the square root of 6. And the second one, a squared plus a is greater than or equal to 5. So we're going to kind of use the quadratic formula to kind of estimate like the boundaries. So a squared plus a minus 5 would be greater than or equal to 0. And if I solve for a, I'll get these two. Again, that's just from the quadratic formula. And here's a little neat trick. We have a greater than sign here. So we know that the region that we're going to take is like the region outside. If I have the number line over here, let's just say this is the smaller root, this is the larger root. And since I have a greater than or equal to sign, these 2 points will be included. And then since it is the greater than or equal to sign, we're going to take the outside region. So this blue graph would be the solution to this quadratic inequality. Now on the other hand, if it was less than or equal to, then we're going to take the region in the middle. So you can kind of use this as a nice shortcut for quadratic inequalities. Anyway, so solving for the quadratic inequality, for the two quadratic inequalities, we're going to get these two as the range of possible values for a. Now, since we know that we want to get the intersection of these two, we kind of have to know where they intersect. So negative square root of 6, that's approximately negative 2.449. So I'm just going to call it negative 2.45. And then this negative 1 minus square root of 21 over 2, you can approximate it to be around negative 2.79. So apparently this part doesn't have a common region with, doesn't share a common region with this blue one. So the intersection of the blue one and this one, we can kind of ignore this already because apparently A doesn't fall into that range. But this range does though, because this value over here, it's actually 1.79, and then the square root of 6 over here, that's going to be 2.45. So apparently the common region of these two these two range of values for A, it's going to be from negative 1 plus the square root of 21 over 2 inclusive up to the square root of 6, so here. Now let us recall the values that we got. We got this to be around 1.79, and this is approximately 2.45. And the only thing we talked about A is that A is an integer. And from this range of values, it is apparent for us to say that A can only be equal to 2 because it is greater than 1.79 and less than 2.45, so it can only be 2. So A, which we know is going to be the floor of x over 100, that's going to be just 2. So we can substitute this number over here to be just 2. So x over 100 times 2, that's going to be x over 50. So the floor of x over 50 is going to be equal to 5. And then we can now get the range of values for x over 50. And it's just one step away to solve the values of x. Since x over 50 is greater than or equal to 5 and less than 6, simply multiply both sides by 50, and we're going to get x is going to be greater than or equal to 250, but less than 300. And this will be our final answer. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye bye!